Wait, just underline this.
Okay, friends, what is weight? Yes.
The force of gravity.
It is the force of gravity.
Relative to you.
Yep. It's force of gravity on an object. What is the unit of weight? The unit of weight is the Newton. So it's force gravity. The unit is the Newton. And that's what weight is. And now we're going to go to page 2. Second page. So page 16. What is mass? Tell your partner, what is mass? Mass is the amount of matter in an object. Okay, so we have the amount of matter in an object. And matter is anything that takes up space and has
volume.
Matter has volume.
Sorry, it has weight. Right?
Has volume. In other words, it takes up space. And it also has mass.
Oh.
Because I can go up into space and not have any weight.
Oh, yeah.
Right?
Sorry. I thought you were defining weight.
Yeah. So matter has volume and it has mass. Now, if you're wondering about like what a gram is about the weight of a paper clip. Okay, so if you can imagine a paper clip, that's about 1 gram. So that's not very much. Okay, a kilogram. I'm going to go grab a few kilograms for you.
Oh,
We're going to pass these around when you're done. Just pass it to the row behind you. We're just going to do one on this side of the room, one on the other side of the room. When it gets to the end, you're going to bring it back to me. That's a kilogram. So that's about 1,000 paper clips.
Oh, it's like satisfying to hold because it's like weighted.
Right? Yeah. And a pineapple is about 1 kilogram. All right? But this is more dense than a pineapple. So mass is all about matter, and weight is all about gravity. Mass is measured in grams and kilograms. Weight is measured in newtons. Which one stays the same in space? Mass stays the same in space. Can you guys even read this? This is cursive writing.
No.
Okay, that says stays the same in space. This one changes in space. It just occurred to me, I'm like, this is a nice like little visual graphic thing that I found, but I'm like, I don't even know if you guys can read cursive, so there we go. All right.
Remember when back in elementary school, they're like, hey, you need to learn cursive because in high school, they're going to make you write everything in cursive. Like, okay, second grade teacher.
Okay, on our next page, we have a little table. And it just says some stuff that we've already talked about. It says that mass is about matter. It's measured in kilograms and it does not change. Whereas weight is the force of gravity. The unit is the Newton, and it depends on where you are. So it depends on the mass and it depends on the distance between the two objects. So it does change. If you have a bigger mass, is the weight bigger or smaller? Bigger mass, bigger force, okay? The greater the mass, the greater the force. Greater the mass, the greater the force, the greater the weight. What do you think about distance? If you have a bigger distance between two things, is the force of gravity going to get stronger or weaker if you have a bigger distance? Think about that for a minute. Like if you think about my pen relative to something with really big mass, like the Earth. But there's some other things in our universe with very big masses. What's something that has a bigger mass than the Earth?
Sun.
The sun. So if I were to let go of this and mass were the only thing that made the difference, this pen should go flying into the sun. Why then does it go towards the Earth? Because it's the closest of the big gravitational pulls. It's the closest big mass. So if you have a bigger distance, what happens to the force of gravity? Does it get bigger or smaller? It gets smaller. Because we're so far from the sun, that's why we don't go flinging into the sun. Isn't that fortunate? Okay? All right, so the bigger the distance, the greater the distance, the smaller the force of gravity. And that means the smaller the weight. So my mass on the moon is the same as my mass on Earth. Yes? I don't know if I weigh 59 kilograms. That's just what the picture said. But my weight, and it sounds weird because we always talk about our weight. I would say I weigh, 100 and whatever pounds, right? But in reality, the unit of weight is the Newton. So in reality, maybe my weight is 579 newtons on Earth. But it's only 96 newtons on the moon. How many times bigger is this? How do you find out how many times bigger something is? If I said, how many times bigger is 100 compared to 25? You would divide. Are you guys okay with putting one thing over top of another for division? Do you do that sometimes? Okay. In science, we tend to do that a lot. We don't tend to write divided by with the divided by and the two little dots. We just tend to put one thing over top of another. It makes it really tidy, and it just lets you put all kinds of things on the top, which you all multiply them, and then all kinds of things on the bottom, and you just divide by them. Okay? So, what is the difference in weight? This is 1/6. How many times more massive do you think the Earth is than the moon? Is it more or less massive, the Earth?
The Earth has more. Wait, sorry. It is more.
It's more massive.
Yeah, it's bigger. It's bigger.
Than the moon,
it's
right?
6 times bigger, right?
Yeah. What if I told you that Mars is 1/3 the mass of the Earth? What would happen to your what would happen to your weight on Mars? It would be 1/3. And what if Saturn is 20 times the mass of the Earth? What would happen to your mass on Saturn? What would happen to your weight on Saturn? It would be 20 times. Yeah, absolutely. Okay. So those two are related to one another. All right. Now, the last thing that we're going to take a look at here is that mass is measured with a balance. Have you guys used balances? Yes, you have. So those are used to measure mass. These are measured in grams. This is called a balance. Now, if you want to measure weight, you want to measure the pulling down force. Okay? So I'm going to go grab a spring scale.
What?
If you want to measure pulling down force, you don't want to use a balance. A balance says, I've got this much weighing this much on this side, and I've got this much on this side, and then to balance out, right? This one you want to measure the pulling force, because this is so simple. Look, it's crazy. But what you would do is you would hang this. I don't know if this one's even going to work. This one's too big for this spring scale. Do you see how it's bottoming out? Okay. So I wouldn't want to use that with a kilogram, but I could say, hang this on here and see if it, and I could measure how many newtons it pulls down with. Yeah? And it's going to say newtons on there. What's this called? Spring scale. Okay? So what do you use to measure mass? Mass is a balance. Weight is a spring scale. Question, do you guys want to see a little video of how a mechanical scale works, like one that you stand on?
Yeah.
Okay, let's take a look at this, because it's actually really kind of cool. At least I think it is. Is this on? No, there we go.
Most scales nowadays are digital. They use electricity to determine how much something weighs. What I'm interested in is these old-style mechanical scales, sometimes called spring scales. No batteries required here. In this video, we'll take apart 2 of these scales to see how they work on the inside. The idea of using springs in a scale has been around for about 200 years now. This one is called a floor scale, and this one is called a hanging scale. So let's spring right into the details here, and we'll start with the hanging scale. These are commonly used at the grocery store. The more weight, or the harder that you pull on the bottom, the more that the red pointer spins on the inside. Take away the weight, and the red pointer goes back to 0. Let's take it apart and see what's on the inside. The first thing you'll notice are 2 large springs on the inside. They are hooked onto the top piece, which is bolted to the frame of the scale. In the center, we have the gear system. This piece is called the rack. Hidden inside of here is called the pinion gear. As the rack goes back and forth, the pinion gear spins too. The rack is bolted to the frame that the springs are on. So when the springs go down, the rack goes down too, which then spins the gear. There's another tiny spring here which pulls on the rack. This ensures that we have good contact with the pinion gear. The center of the gear goes out and pokes through the center of the dial so that we can attach the red pointer. Now as the scale is pulled down, The springs stretch, which moves the rack, turns the gear, turns the red pointer, which then shows how much the object weighs. Now, it may happen that the red pointer starts to get off. It's not pointing directly at 0 when there's nothing on the scale. This might happen when you attach a basket to the scale. In this case, we need to calibrate the scale. That's the job of the calibration knob, also known as a zeroing screw.
Did we have one of those for balance as well? Yeah.
You can see that it goes all the way through and comes out the other side. These two are called the pivot plates. They both have a hole in the middle, which is where they attach. As you spin the calibration knob, it will push against the metal pivot plates. So as you turn the knob, the whole spring assembly will go up or down, which will just barely move the red pointer. Once it's right at 0, then you are ready to start weighing again. The reason that a scale like this works is because of something called Hooke's law. It's the relationship between how much force you pull on a spring versus how far that spring stretches. So just for an example, let's put a 1 kilogram object on this spring. It stretches 1 centimeter. Okay, now let's double the weight. Now it stretches 2 centimeters. For each extra kilogram, the spring stretches another centimeter. If you put it on a graph, then it's a straight line, or in other words, it's a linear relationship. This means it's predictable. We can now use the spring to determine the weight of an object. Figure out how far the spring stretches, which will then tell us the weight of the object. For this spring, the numbers are easy, 1 kilogram for every 1 centimeter. But maybe you've got a really stiff spring. This one takes 5 kilograms to stretch at only 1 centimeter. Maybe you've got a really flexible spring. It takes barely any weight at all to stretch at 1 centimeter. When you study Hooke's law in your physics class, you might see an equation like this, F equals kx. The k is how stiff the spring is. X is how far the spring is stretched, which results in a downward force, or how heavy the object must be. Hooke's law only works up to a certain point. Normally, you take the weight off the spring and the spring goes back to where it started. However, if you put a very large weight on a small spring, you will probably stretch that spring so much that it won't go back. You've reached the elastic limit, and Hooke's law no longer works. This spring is somewhat useless to use in a scale now.
Which is why, when I put this one on here, I kept holding it because I didn't want it to actually bottom out, because otherwise I would have stretched it beyond its stretching point.
So keep that in mind, it is possible to break these scales. With the hanging scale, there's 2 springs in here working together. Since we know how stiff they are, we can use how far they stretch to turn a gear, which then tells us how much an object weighs. Now let's take a look at the floor scale. 2 tiny springs hold it all together. It's easiest to unhook it from the bottom. The front cover comes off and the insides become visible. The big difference here is that instead of a red pointer moving across the dial, this time the whole dial actually moves while the red pointer is stationary. The dial is attached to another pinion gear with a rack moving across it. This, of course, is very similar to the hanging scale that we saw earlier. The end of the rack is attached to a small spring which pulls it towards the edge. Things get interesting at the other end of the rack. We've got a lever that can pivot back and forth. It's attached to the rack, and remember, the rack is constantly being pulled this way. The only thing stopping it is another metal plate right beneath it. This plate is held up by our main spring. There's only one of them this time, and it's quite a bit smaller. Our spring is still hanging, but the end of it is attached to a metal plate. When the plate goes down, the spring is stretched. This also means the lever is allowed to rotate. The metal plate is pressed down by 4 metal bars that go across the scale, 2 long ones and 2 shorter ones that hang right beneath it. All 4 of the bars also rest on the edges of the scale case. The lid to the scale has 4 supports on the bottom. Each of these supports rests on one of the 4 bars in the scale. When you stand on the scale, your weight is distributed down through the 4 bars, over to the metal plate, which moves down and stretches the spring, allows the lever to rotate, which moves the rack, which then rotates the gear that moves the dial.
If you're interested in this kind of thing, you might be interested in mechanical engineering.
No matter where you stand on the scale, your weight gets distributed to the tiny spring, which uses Hooke's law to determine your weight. Just like with the hanging scale, this one may need to be zeroed out if it gets off. The calibration dial is down here. There's two parts to this, the bottom, which can spin, and the top, which fits inside of it. Notice the screw threads around the side. When you spin the bottom, the top goes up or down. This moves the resting position of the spring, which will then ripple through and affect where the dial is when there's no weight on the scale. My name's Jared. I make 3D animations on how things work. If you
Okay. So like I said, if you find that kind of thing interesting, you might be interested in engineering, especially mechanical engineering. There's all sorts of different types, but it's a very practical way of applying sciences to things. All right. Now we have some questions here, which I will let you do for the weekend. But for now, what we're going to do is we are going to go to page 93, jumping way ahead. None of this will be on Tuesday's quiz. Okay, this is new stuff, not on Tuesday's quiz. Scatter plots. Can you guess why they are called scatter plots by looking at these graphs? Yeah. Yeah, all little dots are scattered all over the place, right? And they are really, really effective ways of showing lots of scientific relationships. Do you guys know what we call the vertical axis? That is the y-axis. So the one that goes up and down is the y-axis. What's the one that goes side to side? That is the x-axis. If I have trouble remembering that, I always remember that the y kind of has a part that goes up and down, right? The letter y has an up and down part to it, so that helps me remember. Now, when you graph your data, basically what you do is you say, if I studied on my x-axis, we talked about dependent and independent variables. Yeah? What's another word for an independent variable? Chat with your partner, see if you can remember. You can define it and then you can give another word for it. The independent variable is one that is manipulated. It is the one that you change.
Minutes of studies.
Okay, this is also known as a manipulated variable. Which of our two variables on this first graph, we have minutes of study and we have the test mark, which one is the independent variable? Minutes of study or test mark? Minutes of study, that's the one that's going to have an effect on the dependent variable. Your test mark depends on the minutes of study. That means that our test mark is the dependent variable. And the dependent always goes on which axis? Dependent goes on Y. And that means that the independent goes on X. Now, it's possible that in a graph, that if we look at all of those little points, they generally have an upward kind of a trend. If I drew a little blobby shape here that sort of encompassed all of my points, that blobby shape generally goes uphill, doesn't it? Okay. And when it goes uphill, we call this a positive relationship, because what it means is that as the minutes of study go up, as they get bigger, as they go from 0 to 1 to 2 to 3, as those get bigger, what's also getting bigger? The test mark is also getting bigger. 5, 10, 15, 20. So if it goes up, we say that is a positive relationship. So this is a positive relationship. As X gets bigger, Y also gets bigger. So as the X variable increases, the Y variable also, what happened there? Increases. That's why it is called a positive relationship, or sometimes we call it a positive correlation. Has anyone heard the word correlation before? Little bit? Okay, a correlation is where one thing affects another. Okay? A correlation is where one thing affects another. Oh, actually, no. It's where two things move either in similar or opposite directions. So in a positive correlation, they are both moving in the same direction. But let's say we looked at hours of homework per night. Okay, so we got our hours of homework every night. And then we say, well, if you do more hours of homework a night, what happens to the amount of TV you watch? It goes down. Okay, so watching TV goes down. So what kind of correlation do you think this is? It's not a positive correlation, it's a negative correlation. What's another word we could use for correlation? Relationship. And then finally, we have our shoe size. And we have our average grade point average. So our average grade, depending on our shoe size. What's the relationship there?
Absolutely not.
Absolutely none. This is no correlation. And you can see the points are just randomly scattered. So this is no correlation. Okay. So positive correlation, negative correlation, no correlation. Let's just fill in the rest of this. In graph B, as the x variable increases, so in other words, x is going up, what's happening in graph B? As the x variable goes up, no, that's not the x variable. What's wrong with my brain? That's the y variable. As the x variable goes up, hours of homework per night, what happens to the y variable? It goes down. So the y variable decreases. So when they're moving in opposite directions, that's a negative correlation. When they're moving in the same direction, that's a positive correlation. And when you have a scatter plot, one of the ways that we look at a scatter plot is we will draw little blobby shapes that sort of like encompass all of our points. And then we do our best to draw a line that goes through the middle of that blob. Okay? That line right there is called a trend line. It's got other names though. Does anyone remember them? Yeah. Best fit line. And there's one more, but it sounds almost like the last one. The line of best fit, literally. Yeah. Best fit line or line of best fit. Do those words make sense? Do those words make sense? Because it follows the trend, right? It just shows you where the trend is. Where does that line go? It makes the best fit between those points possible. Okay? And obviously, if we have a blobby shape that looks like this, where is the trend? There is none. It's just crazy. Okay? We have only 10 minutes left. I'd like to give you some time to work on your homework. Okay? Your homework is going to be number 1. Where did it go? Page 19. Pages 18 and 19. However, your vocab quiz is on Tuesday. Do you remember what we learned about spaced repetition? Yeah. What did spaced repetition say? Spaced repetition said if you study once, you'll remember it really well, and then you'll start forgetting immediately. Which means that if you study on Monday night, you might remember it really well for Tuesday, but by the test, you will have completely forgotten it. Yes? So if you study it on Friday, And then you study it again on Sunday or Monday. By the time we get to the test, you'll know a whole bunch more. And if you were to study it on Friday and Sunday and again on Monday, look how much you remember for the test. And you don't have to spend all your time studying that night before the test, panicking, going, oh no, I don't remember anything. There's so much to know. Okay? So try that for yourself. One of the things about your vocab list is that it is foldable. And I know I'm going to fold it one way, but I want to show you the other way it can fold. Yeah. How much should you study for it? You know what? Like maybe I would just be like 10 minutes.
Wait, when is that?
Or, you know, if you felt like after 10 minutes you don't know anything, like I would go further. But, you know, spend 10 minutes on Friday, spend 10 minutes on Sunday, spend 10 minutes on Monday. Meet up tonight and studying for your quiz. Yeah? One of the things you can do with this is you can fold it along the line between the definition and the vocab word. So you can then look at the vocab word and you can be like, oh, what are these things? And then you can go, oh, the answer is right there. Does that make sense? Okay. So I'm trusting you. Oh, and the other thing is I also wanted this weekend to be good for people who were away or whatever and needed to get caught up on some of their homework, you know, because they were missing things. So pages 18 and 19, study for your quiz on Tuesday. And get caught up on anything you're missing. If you had anything on your progress report, get caught up. Okie dokie.
It does the same questions. Oh, that's why. Okay, let's go to I don't know. No, this is send out so what is or I may call appreciation for becoming an experiment. Right? It all makes sense. Yeah, beautiful. If I feel like, yeah. Let's do it.
Like, okay, can I? Tell me what is it? Okay, so a conclusion is the final claim of the scientist made upon analyzing experimental data. I'll probably give you the definition and ask you for the word. Or some people may be like, here's a situation, which of these things is the manipulated variable?
I should just leave these in there over and see what I
Perfect.
Could you tell me the stars again?
Oh, yeah, absolutely. Folks, it's time to get your phone if you've not already done so. Let me just star for you.
Sure, thanks.
Yeah. Okay.
Could I just go grab my phone and stuff?
Conclusion.
Are you looking at my notifications?
Control.
Get away.
What?
Control this.
Why is my phone?
Control variable. Data. The energy.
Oh, did an answer.
Experiment. Experimental group. Fair test.
Oh, we're not
Force.
doing the dependent variable?
Gravity. Huh?
I thought we were doing the dependent variable.
We hadn't covered it as of yesterday, so no.
Okay.
Hypothesis. I've got it on another quiz. Independent variable inference. Manipulated variable mass. Matter. You perfect. Yes. Non-matter observation. Placebo prediction. Yes.
Did I star the right one?
You did. And spring scale and weight. That's it. There you
Oh,
go.
all right, thanks.
Is this your pencil? There you go.
You don't appreciate
Every time I hear that, I think of this song that my son learned when he was in clubs.
On this fence, can I have the note for experimental variable?
Yes, I meant to give that to you after that, so thank you for saying it. Here you go.
Child of being I had keys everywhere. Yeah, keys, Tell you about that. Stop recording.
Pardon me?
I did page 37 42, and I did
Okay.
page 18 and 19 right now.
Okay, I'm gonna get this so I can check those off for you. All
Yeah.
right.
So wait, how much? This won't up my grade by then.
And we had 37 and 42. Excellent.
37,
And what was the other one?
42.
37 and
and
42.
the homework you just gave, 18 and 19.
Oh, okay. That one will
I
be for
just
next
did
day.
that.
Okay, Logan, there we go. Thank you.
I did it. Thank you so much. And
Anything else? You're good.
oh,
All right.
and maybe I didn't take the notes for the first and second page. I just saw
You
it.
want me to just star them real quick?
Sure.
Okay.
I did everything else.
And,
I just want to make sure.
conclusion.
I'll have homework. I'm gonna do
Control.
like days where I do homework. 'Cause
Yeah.
then for band, we just got dropped in playing test.
Yeah. Okay. Control. You're welcome. Have a wonderful weekend. No. Sorry.
Like how we erase it. That's
I
actually
know,
really-
right? It's the best thing ever. Experiment.
Why don't they put that on all caps?
I don't know. They're kind of expensive though.
Oh.
Yeah, I think that's the reason.
I mean, like it's good though.
Yeah. Like I'm willing to pay for it because it makes my life so much easier. Like when I'm marking things, if I make a mistake, I don't have to like scribble it and be like,
Yeah.
sorry, which is what we usually do. And
Yeah,
those
I
are
think
good.
I think I got.
I think you got the
everything else.
rest of it.
Yeah.
Let's just make sure, double check. placebo. Yep. Scientific method. Yep. Spring scale. Weight. And that's it.
All right, perfect.
There
Thank
you
so
go. Have a wonderful
Alright.
weekend, Logan.
much.
Yeah.
Terry Fox went really on me.
Knocked you out. You ran the whole way.
Yeah, I got
Good for
10
you.
minutes.
Nice.
I actually got 3 steps.
Dude, that's fantastic.
So I played basketball at lunch.
Yeah. No wonder you're knocked out, man.
Yeah.
Whew.
I came here, brother. I felt like third period.
Yeah.
Last block. And then I went to bed and Mr. Dudley got mad at me because I was late because I thought that this is my room. You're like, but I was on time. I just went to the wrong room. Come on, church. I don't think you didn't really care. No, I'm like, oh well.
Oh, well. Hey, John.
I just had a question about
Yeah.
this. So, for number 12, the burning match to the wick of the candle.
Yes.
If it's exothermic, it releases energy, right?
Yes.
And endothermic absorbs energy.
Yes.
So if it was exothermic, I know that it gets hot. That means if it gets hot, there's more kinetic energy. But at the same time, I realized that like, if it's releasing energy, shouldn't it have less total energy?
What kind of energy do particles need to collide?
They need kinetic energy. Oh, I see. So
So what's
potential energy-
happening is there's potential energy and it's being converted into kinetic energy, which
Yeah.
makes the particles
And
move
some-
faster.
and some heat energy, I guess.
Well, heat really is
Kinetic.
kinetic energy in a way. Heat is the movement. What heat is the movement of that energy from one place to another place. That's what heat really is.
So
Heat's a kind of a funny word, right?
yeah. So the lighter gives basically the whole like candle wick system more total energy, and then when it starts the reaction,
Yeah, it gives more kinetic energy, right? So it provides it
Yeah.
it gives that extra energy into the system. And then the system itself starts turning potential energy into kinetic energy, which makes the particles move fast enough that they can have that activation energy.
I see.
Yeah.
And for this one, can we use the mass of calcium of this?
You could. It will be an ugly, messy mess. So this is like putting chalk in acid. You can
Yeah.
imagine how lovely that's going to be at the end.
Oh, I see. So
Right.
we could, but it's not the best.
Yeah, exactly. Because you've got a gas escaping. Why not just stick the whole mess onto a balance?
Yeah. Also,
Yeah.
is this the same question as?
Oh, it
the one
very well
before?
could be. Yeah. Okay, I need to remove question number 4 or whatever the other. Number 4 is a repeat. Let's put that in there.
And sublimation, is it from gas to?
Sublimation
Oh,
is
it's
from solid to gas.
okay.
Yes. Yes.